Have you ever wondered how we measure the physical quantities around us? Let's take an example to understand this better. Consider a table in your room. How long is it? To quantify this, we measure it in a standard unit, the meter. So, let's say the table is 1.5 meters long. In this case, 1.5 is the numerical value and meter the unit. This is how we quantify physical attributes of objects and phenomena around us. Now, let's delve into the concept of significant digits. These are the digits in a measured value that are believed to be reliable and add to the precision of the measurement. Any non-zero digits, zeros caught between non-zero digits, and trailing zeros on the right side of the decimal point are deemed significant. Let's consider the number 200.3 for instance. Here, every digit is significant except for the leading zero. The leading zero is deemed insignificant as its primary function is to help position the decimal point. Next, let's apply these concepts to a practical example, measuring the length of a pencil. We will use a ruler with a least count of 1 millimeter. Precision comes into play when we repeat the measurement. If we consistently get the same value every time we measure, then our measurement is said to be precise. Remember, the precision of a measurement is determined by the smallest division of the measuring instrument, which in this case is the least count of 1 millimeter. This allows for more precise measurements than a ruler with a least count of 1 centimeter. To understand the concept of the least count, consider a thermometer that has a least count of 0.1 degrees Celsius. This essentially means that the smallest increment in temperature that this thermometer can reliably detect is as minute as 0.1 degrees. The least count is thus the smallest division on the scale of any measuring instrument, representing the minimum variation that can be accurately measured by the said instrument. Finally, we'll delve into accuracy. Let's understand it better with an example. Suppose we are measuring the temperature of boiling water, which should theoretically be 100 degrees Celsius. Accuracy comes into play when our thermometer reads 99.9 degrees Celsius, signaling that our measurement is incredibly to the true value. This closeness of a measured value to the actual value of the quantity being measured defines accuracy. An accurate measurement is one that mirrors the true value with barely any error. The degree of accuracy is swayed by factors like precision and systematic errors. Systematic errors are those persistent, repeatable mistakes that are born from factors such as faulty calibration of the measuring instrument or improper technique. In contrast, errors are unpredictable, differing with each measurement. To enhance accuracy, it becomes pivotal to shrink systematic errors and curb random errors by calculating the average of multiple measurements. Summarizing our discussion, let's take on a practical approach. Imagine measuring the length of a table, the temperature of boiling water, or the length of a pencil. These real-life examples give us a chance to apply standard units and realize how significant digits help us determine the precision of these measurements. The exactness and precision of measurements are not just random, but are governed by the least count of the measuring instrument we use. They are also highly influenced by our ability to minimize systematic and random errors. So, the next time you're measuring anything, observe how these principles come into action.